we're up to our last video on covalent properties and covalent molecules. It's been a big chunk of Area of Study 2 and Unit 1, and that's what most of your questions will end up being on. So what we're going to start with is we're going to summarise from the weakest to the strongest forms of bonding between nonmetals. So, and of course it's going to freeze on me, so you can't see what we're looking at. Let's look at it again. Here we go. Nice. Let's just go out of here. Here we go. That's much better. So here are your order of bonding strength. So your weakest ones start up the top with your green, and they are your dispersion forces, or the instantaneous dipoles within the molecules that create dispersion forces. These are a form of intermolecular bonds. Then you have your dipole-dipole bonding. So now we're working with polar molecules. These are ones with differences in electronegativity and asymmetry. And these are also intermolecular forces. After that, the next strongest are your hydrogen bonds. These are the dipole-dipole bonds that happen with hydrogen, fluorine, oxygen, and nitrogen. And then the last one is covalent bonding. And covalent bonding is an intramolecular type of bond, and therefore it's really, really strong. And so here is your order. Now, the evidence for the bonding in this order is the fact that we're melting and boiling points are quite low of things that only exhibit dispersion forces, all the way up to hydrogen bonding where they get a lot higher. And then if you are trying to actually decompose or split apart a molecule by breaking apart its intramolecular bonds, that's going to take a lot more energy. So the evidence for the bonding in this order are the melting/boiling points. As the bonding strength increases, the melting/boiling points increase also. Yay. So I want you to stop and I want you to think about this table, which is again not showing up for you. We've got having a fun time with our Zoom today. All right. So with this table here, you can see, I want you to pause and have a think. What have we got that our relationships are? Is this going to follow all of those patterns that we just talked about now? So you've got hydrogen, fluorine, and carbon dioxide, the top three here. So these three here, we've got hydrogen, fluorine, and carbon dioxide. What do we know about these? These are all non-polar. Okay, so all of these molecules are non-polar, therefore they have dispersion forces only. Dispersion forces only between those molecules. The next three, as we go down, we've got hydrogen chloride, hydrogen bromide, and hydrogen iodide here. Now we can see automatically that their boiling points and their melting points are a lot higher than the previous three. So these are now polar molecules because we've got a difference in electronegativity and we're asymmetrical, but there's no hydrogen bonding. So what we've actually got here is we get both dispersion forces and dipole-dipole bonding here. Okay, so this is the bottom of those notes. It says HCl, HBr, and HI are all polar molecules. Therefore, they experience both dispersion forces and dipole-dipole attraction holding them together. This is stronger than dispersion forces, those yellow ones above. And note that the melting and boiling points of these increase as the molecular size increases. So here we've got molecular size is also increasing, and you can see that those MPs and BPs are also going up. As size increases, there are more electrons. The more electrons there are, the more dispersion forces there are. Therefore, you get more energy to split apart those intermolecular bonds. Now, the last two here, we have ammonia and water. All right, these are our last ones here. They have much higher melting points, much higher boiling points, considering they're both quite small molecules. So these ones have got hydrogen bonding. What that actually means is they've got hydrogen bonding plus dispersion forces. Because remember how we said that everything is going to have dispersion forces. But these ones have the H bonds, which are the strong types of dipole-dipole interactions. So the last paragraph there says, lastly, water and ammonia both experience hydrogen bonding, H with F, O, or N, as well as dispersion forces. And hydrogen bonding is the strongest form of intermolecular bonding. Hence, they have the highest melting and boiling points. Okay, while we're here, let's finish it off and let's think about, again, it says whiteboards. Normally I get you to do this in class. I want you to pause and think about if they have a low melting boiling point, what is the inference we can make about that? What does that mean about the forces or the bonds that exist within that molecule? Same with how hard they are. Is there anything that we can go for? Focus more on the fact that they're soft. Are they malleable? Yes, they're quite malleable. Why would they be malleable in terms of these intermolecular forces? And they are non-conductors of electricity. So tell me why. So give it a pause and then come back and see if you got your inferences right. Welcome back. Let's have a look at our table. So the reason they have low to moderate melting points or boiling points is that they have these weak intermolecular forces, therefore not much energy to separate the molecules. Yeah, so that's a nice explanation there. Why aren't they very hard? Again, those intermolecular forces are quite weak. So therefore it's harder to keep molecules together. So they're soft. They can be easily kind of moved around on top of each other. The next one is why are they malleable? It's pretty much the same as before, but this one's got a little bit more explanation in the box. So the forces of attraction between those molecules are not significantly disrupted if you move them around. Because they're just weak intermolecular forces, if you move them around this side, okay, I'm not that upset. It's non-directional, or it's pretty much non-directional. There is some directionality to it, but because of the nature of them being able to move around each other, most of the time they're gases, or even if they are a solid, you can kind of move them around. So if we were at school, I could get some dry ice and I could crush it up and show you that it's actually very easy to kind of crush it. I know malleability is usually something we reserve for metals, but dry ice itself, which is solid carbon dioxide, is quite malleable. Like you can just push on it and it bends or reshapes itself. The last one is why aren't they conductors of electrical signals? And this is because we've got, again, no free moving, and there's also no charged particles. So they don't have either. So therefore, no electricity. And that is officially the end of covalent bonding.